So this review is on chi-squared test. Just to sort of review a couple of things at the very beginning, just remember the chi-squared distribution is different than a t-distribution or a normal distribution. It only has positive values, and it is skewed to the right. It is not symmetrical. So remember, when you draw it, you're going to draw a backbone so they can tell that you know that it's only in the first quadrant. How skewed it is completely depends on its degrees of freedom, which is the number of categories minus 1. As the degrees of freedom increase, the graph becomes more bell-shaped and looks more symmetrical. So as your number of categories get bigger and bigger and bigger, your degrees of freedom are going to get bigger and bigger, and it's going to look more normal. A couple of things to point out: that the mode, which is the high point, occurs over n minus 2. So the number of categories minus 2. I think I put that fact on here because I saw it in a multiple choice question once. So just a nice little super detailed fun fact. The p-value is the probability of getting a value of chi-squared as large or larger. So you are always right-tailed. If you'll remember, your h sub a is not a greater than or less than or not equal to, and we'll go over what those are, but there's no inequalities in here. These are always right-tailed. To find your chi-squared p-value, you're going to do chi-squared CDF, lower, upper, and then degrees of freedom. And then to clarify, when we use a chi-squared test for goodness of fit, it's when you have categorical data describing one variable. You can use the numbers to think of like a percent or a proportion, hair color distribution in a school, number of students in each AP class, types of trees in a forest. The one I always think of is the M&M problem, where they gave us what the distribution of colors of M&Ms should be, and we compare that to what was in our bag of M&Ms. Not averages, lengths, or anything quantitative. It must be categorical. So think about proportions or percents. Okay, this is your study guide, which you already have. So this compares all three in one swoop. So we'll just kind of go over these real quick. Make sure, I think the biggest challenge on these is knowing which test to do. The chi-squared test for goodness of fit, to me, is the easiest because it's the only time you have a one-way table. The homogeneity or the independence, you have a two-way table. Okay, so to know the difference between the two, for homogeneity, you have to have two populations, two separate populations, and one variable. For a independence test, it's a two-way table. So you have one population and two variables or treatments. Okay, now an example pops to mind where we were doing something with gender and something about scary movies, I think it was. And it said that you took a sample of 1,000 people and then separated them by gender and how they reacted to a scary movie. That's one population with two treatments. But if I arranged my study so that I took 500 women and 450 men, then that's now two populations, one treatment. So you have to really read about what their sample is coming from, if it's one population or two. Okay, so for goodness of fit, your H sub O is the distribution fits, or the blank are equally likely among blank. The blank are uniformly distributed among blank, or the distribution of blank is the same as blank. Again, the one that comes to mind is the M&Ms. And you would use this last one. The distribution of colors of M&Ms is the same as the distribution claimed by the manufacturer. Then there was one, about astrological signs, and if they were, if you're equally likely to have each astrological sign. So that would be the second one. The astrological signs are uniformly distributed among all, U.S. citizens. So those are your H sub O's, and then your H sub A is that it doesn't or it isn't. And a lot of times you can get that sentence from the question. For chi-square test for homogeneity, the distribution is the same for both populations or there is no difference. Homogeneity means that they are the same. So you can say that they are the same, the distribution is the same for both populations. Remember, one variable, two different populations. So you're saying that men and women's reactions to scary movies are the same. And then your H sub A is that they are different or that there is a difference in. Chi-square test for independence, if you have one population and two variables or treatments, this is independent, so you're going to say blank and blank are independent. Gender and reaction to scary movies are completely independent, or they are not independent. There is not an association, or there is an association. And again, that's when you would have one population and two variables. So that's when gender would have been looked at as a treatment. Random, independent, and large counts condition. Random for all of them, independent. Obviously, when you have two sample sizes, which you only have here, both these only have one sample, one population. And then your LCC, your large counts condition, all expected counts have to be greater than or equal to 5, and you're just going to show that in the table. To get your expected counts, you're going to use your percent times your sample size. So like if we were doing the M&Ms problem and they said 12% of the M&Ms are blue, and I have 50 M&Ms, then I would do 0.12 times 50 to get its expected count. If it's evenly distributed, and I take my population, let's say we're going to find 100 people, and the number of categories, we have 12 astrological signs. So I would divide it by 12 and see what it is when it's evenly distributed, uniformly distributed. If you have a two-way table, and again, this is not on your formula sheet, you have to do row total times column total over the total total. So row total times column total over the total. And you're going to write that formula down. Anything that you think or use, make sure it gets written down. This is on your formula sheet. Do not have to memorize it. Remember, you're going to show a few by hand. Don't forget your sigma. Show a few by hand with a dot, dot, dot in between. And then to do these, you're going to go put your data in L1, your other data into L2, your observed into L1, your expected into L2. And then in your L3, you do L1 minus L2 squared over L2 and hit enter, and that populates it with your L3. Let's see. Then, after you have that in your L3, you're going to do one variable stats on your L3, and you're looking for the sum of all the x's, not the sum of x squared, just the sum of all the x's. I just want the sum of that formula. Let's see, p-value, obviously you're going to draw a graph. Your degrees of freedom, well, when you're a one-way table, it's just the number of categories minus 1. Degrees of freedom, and this is something, don't get confused with a two-sample test or a two-sample interval where you take the smaller sample size and subtract 1 for your degrees of freedom. For chi-squared, it's number of rows minus 1 times your number of columns minus 1. Degrees of freedom are usually very small for chi-squared tests because it has to do with the table, and usually they're not going to give you a ginormous table to do one of these. And then you do your chi-squared CDF from your chi-squared that you get from here to infinity, and then put your degrees of freedom in there. And then since our p-value is greater than or less than the level of significance for this test, we either reject or fail to reject h sub 0. There is or is not enough information to conclude that whatever h sub a is, our data is or is not statistically significant. So pretty straightforward. Again, if I were you, I would focus on the when to use what. So that row right there, I think, and your hypotheses, I think. Everything else should be pretty straightforward pretty robotic at this point. Okay, so let's just talk through, I think I have 3, so one of each, and I'm going to go really fast. But again, this is just to sort of get it back on your brain. All right, which modern electronic device do you most care about? A simple random sample of 120 people were asked 2 questions, their age, and if you have to give up one of the 3 electronic devices or services for 3 months, which would you choose to give up? Okay, so I'm already seeing I have 120 people. That is one sample. And then I have 2 variables. I have your age group and which service would you give up. And I can see that I don't have 3 separate populations because I only had 120 people. So I have one sample, 2 variables, so start to think about which one that is. It says, does the sample provide convincing evidence of an association between age group and which service someone would give up? Okay, well, I'm looking for, is there an association? Okay, so this is a chi-squared test for independence because I have one sample and 2 variables. My null and my alternate. My null is going to be, and again, I'm looking for evidence of an association. So my null is there's no association between age group and which service they would give up for 3 months in the population of all people who use all 3 services. And again, that's just going back and not being lazy and making sure you really nail down who this population is. Independent. So again, are these 2 variables independent or not? H sub A, there is an association. I'm going to set my alpha at 5%, and I'm going to check my conditions. Random, it said that it was a random sample. Independent. Now, this is the one, I don't know if y'all remember, but it had 120 in the problem, but it's 100 here. So it says only people who actually owned all 3 devices were interviewed. So we sampled 120 people. Apparently 20 of them didn't use all 3. So I only have 100 people in my sample size. If you didn't catch that and put 120 there, I don't think it would kill you. I don't think it would drop you a whole point. But I think it could gather with some other tiny careless mistakes and accumulate to a whole point. So I have 100 less than or equal to 1/10 of the population is good, and my large count, all expected values greater than or equal to 5. So to get the 16.32, I'm doing the column total times the row total, hitting enter, and then dividing it by the total. And that's where all these numbers are coming from. So this one right here would come from 51 times 39, hit enter, and then divide it by 100. Okay, so now that I've done my conditions, I'm ready to go to chi-squared. I'll write my formula. I'm doing a couple, look where these numbers come from, over that, and then a little dot, dot, dot. But then I went straight calculator, and I put my 24, 27, 5, 13, 8, 3, 6, 14, all in my L1, and then all of these went in my L2. Then I went up on my L3 and did L1 minus L2 squared over L2. Then I did one variable stats on my L3, and I'm looking for the sum, and that's where that number comes from right there. You can pause this and type that in. You're going to have a chance to do that on your homework. So if this sounds really familiar and you feel pretty good about it, I wouldn't worry about typing this one in, like I said, because you're going to get practice when you do your homework. So now I have my chi-squared. I draw my chi-squared curve. Put my number, shade to the right. Always, always, always shade to the right. I show my degrees of freedom formula. I have 3 columns and 3 rows, so this is going to be 2 times 2, which is 4. There's my chi-squared CDF, and there's my tiny p-value. Okay, so since our p-value is less than the level of significance for this test, we reject H sub O. There is enough information to conclude, and then I just go back and read my H sub A. There is an association between age groups and which service they would give up for 3 months in the population of all people who use all 3 services. Again, don't be lazy right there. Our data is statistically significant. All right, so that was an independence. Okay, in a certain voting district, the proportion of voters who registered as members of specific parties are as follows. So these are the proportions of registered voters of particular parties in a certain voting district. In the most recent presidential election, again, that's a place where we can't be lazy right there, a random sample of 400 voters surveyed as they left the polling place said they voted for the following presidential candidates. Do these data provide evidence that voters in this election did not vote accordingly to their registered affiliation? Support your conclusion with the appropriate statistical test. This is a one-way table, so this is absolutely a chi-squared test for goodness of fit. I want to know if this fits this, or the other way around. I want to know if this fits this. Okay, so here we go. H sub O, the distribution of political parties of all voters who voted in the most recent presidential election, again, don't be lazy, is the same as the distribution of people registered for each party. Be very careful about your wording and make sure it makes sense. Your H sub A, the distribution of all political parties of all voters who voted in the most recent presidential election is not the same. I set my alpha at 5%. And now I'm ready to check my conditions. Random, it said that it was a random sample. I'll only have one sample size, 400, and that would just be all voters. Probably all voters in this district. Large counts condition, see table. Okay, so make sure, let's figure out how we came up with these numbers. Okay, so I had 400 voters, and these are the percents that it's supposed to be. So all I did was 0.48 times 400 and 0.43 times 400, because what these numbers are my expected. This is observed. That's what actually happened. Expected is what should I have expected to happen. So it's the percents times the total number of voters. Okay, once you're done with your conditions, you go to your formula sheet. Write your formula. Always label it chi-square. Don't give me a floating formula. Throw some numbers in there, little dot, dot, dot in the middle, and then go to your calculator, and you're going to get your chi-squared. Then I find my p-value. Show my degrees of freedom, categories -1. Draw your chi-squared distribution. Then chi-squared CDF from my chi-squared to infinity and then my degrees of freedom. T tiny p-value, and so now I'm ready to make my conclusion. Since our p-value is less than the level of significance for this test, we reject H sub O. There is enough convincing evidence to conclude that, and then go get your H sub A. The distribution of political parties of all voters who voted in the last presidential election is not the same as the distribution of people registered for each party. Our data is statistically significant. Now, it's not asking us which one was more, which one was less. It's just, is it the same or is it different? That's it. And be real careful not to interject too much information, or by all means don't interject your opinion unless they ask for it, which they probably never will. Okay, last one. A large company planning to install drink vending machines in its office building selects simple random samples of both professional staff and the administration support staff and asks people to choose between two brands of drink machines, Coke or Pepsi. Here are the results. Okay, now hold on a second. Let's go back. Selects simple random samples, more than one sample, of professional staff and administrative support staff. So we have two samples here. Two samples, one variable. Professional staff is one sample, support staff is another sample. So two separate populations here. Do these data provide evidence that there is a difference in the brand preference of professional and administrative support staffs? Okay, so I have two samples, one variable. So think about which one that would be. And that's a chi-squared test for homogeneity. Two populations, one variable. Again, I hope you can see that once you figure out what this is, the process is very simple, I think. Again, a little robotic because we've done it so much. But what you need to focus on seriously is reading the question and knowing what kind of test it is and being able to form your null and your alternate. That, I think, is the kicker. Okay, so my H sub O, the distribution of drink brand preference is the same for both professional and the support staff at this large company, and your H sub A is that it's not the same or that it's different. Again, homogeneity is going to be the same. Note this does not state that the number of people who like Coke and Pepsi is the same, but the distribution of preference is the same for both populations. So it's not about the number of people who like Coke and Pepsi being the same, but the distribution of preference is the same. Real quick to do your conditions. Now remember you have two sample sizes. So random, yes, it says it's a simple random sample. Independent, you have to do this twice because you have two separate populations. I have all professional staff and also support staff. And you put your check mark and just assume. Large counts condition, let's check it. To get these numbers, just make sure you're cool and understand how to get those numbers. You need your totals, which they didn't give you. A lot of times on a two-way table, they're going to give you your totals, but they didn't give you totals on this one. So again, remember it's column total times row total over total total. Then I go to my formula sheet. I get my formula. I went ahead and showed them all by hand because I usually do two at the beginning and one at the end, and that just left one out. So I just went ahead and showed them everything. But to actually find this number, I did L1, L2, and L3. Come over here to find my p-value. Don't forget to shade. Show my degrees of freedom formula. There's my chi-squared, and there's my p-value. All right, now this p-value is 0.06. So since this p-value is greater than the level of significance for this test, we fail to reject H sub O. There is not enough evidence to conclude, and then you go get your H sub A. There's not enough evidence to conclude that the distribution of drink brand preference is not the same for the professional staff and the support staff at this large company. Our data is not statistically significant. Just want to remind you, some of you are getting kind of bumfuzzled a little bit right here. There is or is not enough evidence to conclude that whatever your H sub A is, if you reject it, or if you reject it, then there is enough information, because you're rejecting H sub O, there is enough information to go with your H sub A. If you fail to reject it, then there is not enough information to conclude H sub A. But your conclusion is all about, are you going with H sub A or are you not? And our data is not statistically significant. So again, if you're going to stare at something for this chapter, I would stare at the one-way and the two-way tables, the how many populations, the how many variables, and your null and your alternate statements.